Imagine taking every atom in the observable universe and counting them. You'd get around 10 to the power of 80. That's a 1 followed by 80 zeros and is actually equivalent to my bank account debt. But if you go even further and break them down to elementary particles, there are still only around 10 to the 86 to 97 in the entire universe. In other words, there should be no physical quantity ever greater than 10 to the 97. Past this, numbers stop being countable things and start being ideas. Yet beyond the largest of ideas lies infinity, so impossibly big that there is no real parallel. And that's where some people take issue. These people call themselves finitists. As the name suggests, they emphasize everything is finitely defined and subsequently, they want to kill infinity. But does their argument have any merit? I mean, infinity does exist, right? Well, let's try to put ourselves in the mind of a finitist and see if this new perspective holds any interest. Alright, infinity is gone, but not entirely. Finitists still need to deal with obviously infinite things like the set of natural numbers or points in a line, and they honestly have a pretty clever philosophical explanation. The first rule of being a finitist is that only finite mathematical objects exist, and all reasoning must be grounded in finite construction. What this means is that any mathematical object must be defined by finite processes. For example, natural numbers can be defined by adding 1 repeatedly, which mathematicians can use to get any number no problemo. This is called a potential infinity, the idea that something can theoretically go on forever, never reaching an end. However, as soon as you claim this infinite process is completed and collate every natural number into a set, finitists lose their mind. This is not a mathematical object, it is incomplete. How can you claim to have reached the end of this infinite chain and somehow fit it into a packaged object? While they allow potential infinities like adding 1 recursively, they reject actual infinities or a completed infinite totality. And I'm sure you're curious about other things like digits of pi or points in a line. Pi, Euler's number, root 2, all of these irrational things are not seen as infinite decimals. Instead, they are treated as finite descriptions of rules or algorithms that can generate rational approximations to any required finite precision. For example, while a computer can calculate pi to 10 digits, and if they wanted to could go to 100, in no case can it actually reach the true infinite digit count. Once again, they are potentially infinite, but never actually infinite. Really try to understand this as a new finitist. For the remainder of this video, unless something is defined finitely, that thing no longer exists as a completed mathematical object. Okay then, we've established the key idea behind their philosophy. Let's explore how they navigate this much more restrictive mathematics. One of the most interesting challenges of finitism actually lies in geometry. Although geometrical quantities are usually of a finite size, their space is continuous. If you took any 2 distinct points in that space, there are infinite points that lie on the line segment between them, making all measurements violate the basic rule of finitism. Finitists sidestep this actual infinity by dividing space into discrete units called hodons, which are essentially the smallest possible unit of space, kinda like a spatial atom. A great example of hodons in use would be your everyday ruler, measuring and rounding length to a hodon of 1 millimeter. Similarly, area is approximated into 2D hodons by pixelation, and volume by counting 3D hodons, or voxels. Once again, this is a process that can potentially go on forever, giving the measurement to any required precision. At this point, you probably realize how much harder it is to do things as a finitist. Even something like finding the area of a circle now requires algorithms to break it down into hodons. And that's one reason finitism struggles in higher mathematics. But interestingly, the same limitation is exactly why its ideas thrive in computer science, which can only work with finite representations. But let's not get sidetracked. Finitism is still mathematics, and math has paradoxes, a good portion of which are created and resolved by infinity. But finitists can't use infinity, so they created some pretty interesting ways to avoid paradoxes altogether. A famous example is Zeno's racecourse paradox, arguing a runner can't ever finish a race, as to do so they would need to travel half the distance, then half again, then so on to infinity. The paradox is that completing an infinite number of tasks should be impossible in a finite time, which is usually resolved by explaining the time taken for each task gets smaller and smaller, eventually converging to a finite value at infinity. But finitists? They say screw that. Space is made of discrete quantized units called, you guessed it, hodons. The runner doesn't need to complete infinitely many tasks, they simply cross a finite number of hodons to reach the finish line. Boom, paradox solved. Another fun example is the Grim Reaper paradox, where an infinite sequence of Reapers are each assigned a time to kill a person, say Bob. The rules the Reapers must obey is that the Reapers can only kill Bob if no Reaper has already killed him, and each progressive Reaper kills Bob at an earlier time. Say Reaper 1 kills him at 1 PM, but Reaper 2 kills him at 12:30, then 12:15, and so on. The result? No Reaper can act, as the one after them would have already killed Bob at an earlier time. But the paradox is that Bob also can't survive past the latest scheduled time of 1 PM. So he's simultaneously alive and dead, but in a different way to Schrodinger's cat. Finitists handle this paradox with a special tool called causal finitism. Causal finitism is an extension of their rule, arguing no single effect, in this case killing Bob, can have an infinite chain of causes. As soon as causal finitism is introduced, the paradox vanishes, because the scenario can't exist. As lazy as this seems, it stays consistent with finitism as a whole. In their restricted framework, there are simply infinite things they don't need to deal with or consider. Now that you are a baby finitist, you're probably wondering what the mathematical community thinks of your philosophy. Well, it's interesting. While finitism has found applications in computer science, most mathematicians still see it as a niche philosophical stance, incapable of tackling higher mathematics. Yet there's an undeniable beauty regarding the finitist determination to question infinity. Regardless of its practicality, finitism shows that mathematics isn't just about cold logic. It's about how we choose to engage with the infinite possibilities around us every day.